Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh, and a very good day to everyone. For this session, in this video, we're going to discuss on the next chapter for this subject, in which we are looking at the generation of high voltage. Right. So for this topic, before I proceed with the topic, I would like to acknowledge that these notes on this slide presentations is belong to Dr. Nordiana, and thank to her for lending this notes to share this note to be used by us, by me and by the student. Alright, for this topic, we're going to discuss on three main high voltage categories, in which they are alternating current, AC, direct current, DC, and impulse voltage. Alright, for AC, this is the most high voltage AC, HVAC. And these are the most commonly used in practice by the power provider. And those for the HVDC and impulse, these are commonly used for laboratory purpose, right? For testing and to be used in the laboratory. Okay, overview of high voltage applications. All right, high voltage, we can classify the high voltage into the three main categories, as I explained before. High voltage direct current, HVDC, high voltage AC, in which we are going to look on the high frequency and the power frequency. Okay, power frequency is 50 or 60 hertz, as we already know, and high frequency for the laboratory test purpose, so that we can further validate the functionality of any device or installation purpose that been developed. Alright, high transient. The impulse voltage is also called the voltage under transient conditions. In this case, we are going to look at the two most commonly phenomena, which are lightning and switching. Okay, and high current. Okay, we're not going to look in detail on this high current because this is rare in practice, and probably as additional knowledge to everyone. High current for AC, DC, and impulse. Okay, generation of high voltage alternating current, HVAC. Okay, basic principle. Okay, as we already know, and as everyone might know, how to generate the high voltage is simply by using the transformers, right? We use the transformers, step-up transformers, to lift up the voltage level. Okay. And then, okay, for the transformers, general characteristic for the transformers, we have the three-phase and obviously single phase. And the single phase is normally used for testing in the laboratory. And for the three-phase is been commonly used for in practice by the power utility. Okay, okay, at same voltage level, okay, at same voltage rating, okay, normally testing transformer will have much lower kVA rating, right? Testing, okay, for the same voltage rating, a much lower testing transformer will typically have a much lower kVA as compared to the power transformer. Why? These are two categories. We have the testing transformer, and we also have the power transformer. What are the difference between these two transformers? Okay, first, the testing transformers been used in the laboratory for testing, and then the other one, power transformer, is the one that been used by power provider and been installed or been deployed in applications, right? So why the kVA? Why at the same voltage rating we gonna have the much lower kVA for testing transformer? One of the reason is that think maybe in the next slide. Okay. Okay, one of the reason is that we for the same voltage level we have a lower kVA is because okay, for testing purpose we going to use it for testing, and then means that we not going to use the transformers for a very long period of time. Okay, as compared to the power transformer, in which once the power transformer been installed at any location for applications, the transformer will run 24/7 for say 1 year, 2 years, 3 years straight, depend on the application or service and maintenance, right? Okay, in which for the testing transformer we will use once a while in the lab, or maybe we'll just use maybe for a short while, 1 hour, 10 minutes for each testing, right? So so we don't want to compromise. Okay, so for the testing transformer, cooling of the winding will not be a major problem. Okay, we know it's a testing transformer, so we don't worry too much on the cooling, since and some more we have a much lower kVA rating as well. All right. And the flux density in the testing transformer, okay, is kept lower than the power transformer. Okay, why we try to restrict the flux density in the testing transformer? The reason is that we don't want the high magnetization current that will cause this harmonic distortion to the output voltage during the test. Okay, we want to perform the experiment. If the flux density, if the harmonic distortion is too much, is too high, we unable to capture the output or the testing output accurately. Okay, that's why as compared to the for the same voltage rating, a testing transformer will have a much compact design if compared to the power transformer. In comparison, maybe I can say we have the power transformer of Velfire size or Toyota Alphard size of the power transformer, but for the same voltage level, and we might have a very I would say a wheelbarrow size for the testing transformer. That is the difference. Why? We don't need to worry about the cooling system, and we don't need to worry about the high kVA, high power rating. Okay, that is why the testing transformer will have a much compact design if compared to the power transformer. Okay, this example of the testing transformer. Okay, testing transformer, we have a tank type. Okay, we have a tank type, and we have insulated enclosure type. Okay, this is the one that we have in the high voltage lab, right? We have the insulated enclosure type. Okay, if you can see, this is the cylindrical shape, the one that we have in the high voltage lab, if you have seen that. And then we have the iron core here and the winding. Okay, low voltage and high voltage winding, iron core, and normally we will have the insulated enclosure. Okay, insulated enclosure, we have the base, and we have the high voltage terminal, in which we plug in we put in the metal conductor here, and then we will have oil inside here. Okay, this is the cylindrical type or insulated enclosure type, and this is another type, a tank type. We have a tank, relatively smaller if compared to this one. We have almost the same size of this, but relatively compact. But for this one, we have the bushing. We would require the bushing, and this is the high voltage terminal. Okay, so we can really see the difference between tank type and insulated enclosure. But we can say that both of this testing transformer can carry the same voltage rating and kVA. The difference is just the construction design. The one that we have in the lab is this type. Okay, a tank type, core. Okay, just to describe the difference between these, if you can see carefully, okay, the core and the winding are enclosed in the metal container. Tank type is a metal container, while the insulated enclosure, the enclosed by the insulated materials. Okay, so what is the reason for this transformer to have metal container? Is because it need to provide a natural cooling to the oil within the transformer. Means that we have a metal, the metal will contact at the ambient temperature, and then metal, as we know, is having a good thermal conductivity. So hopefully the cooling of the metal will effectively cool the oil within the transformer. Okay, and problem is that we need this would require a bushing that will increase the cost to the construction design, and large space, obviously. Okay, because this transformer, tank type transformer, relatively higher, and when it become higher, we need a clearance that is bigger. That's why we might need a bigger space as compared to the insulated enclosure type. Alright, so we might need a relatively bigger clearance distance as compared to the one. Okay, as we compare this one, a less quantity of oil. If you can see this comparison, the oil, if you can see here, tank type, the oil space is relatively lower as compared to this one, in which this one need to be filled by oil. Alright, heat dissipation through the insulating enclosure, through the metal. Okay, heat dissipation through the metal. This is typo, and this one requires bushing. Right, and for the for the insulated enclosure, insulated cylindrical shape here, large oil of quantity, as I explained before. Okay, high thermal constant. What is mean by high thermal constant? Means that the thermal constant for this the thermal conductivity is relatively not effective as compared to the tank type, and small heat dissipation, since this one made of the insulated material, so the heat transfer from the oil to the environment is less effective as compared if this one made of the metal. Okay, and this one no bushing, is more compact, if you can see, and and since it has no bushing and relatively smaller in size, so the clearance for safety clearance for this transformer is relatively smaller as compared to the tank type. Okay, now we're going to look at the high voltage AC generator. HVAC generator. How to generate high voltage alternating. Okay, first we have the straight transformer. Number 2, we have cascaded transformer. And number 3 is resonant. Okay, resonant. Okay, in short, just to differentiate these 3 transformer, is that straight transformer is just a single unit of the transformer. Cascaded, in order to generate a much higher voltage level, we may need to combine the several unit of the straight transformer. For example, the straight transformer with the power rating about 100 kV, once we cascade another single unit will have 200, we add on one more will give us 300. As simple as that. I will justify or explain later. And resonant transformer is that the transformer that is been modified for a certain reason that I will explain later. Okay, a straight transformer. Okay, it's just a normal step-up transformer. Normal step-up transformer. Okay, obviously we'll have a high voltage potential and low voltage potential being grounded, and we have the iron core, and the tank also will be grounded with it. And low voltage winding, low voltage winding, for this one, low voltage winding can be connected to the voltage regulator. Why we need to connect the voltage regulator to the low voltage winding? Okay, what happens is that the transformer will have primary winding and the secondary windings, and then primary input, secondary input. The only way for us to varies the voltage output is to varies the voltage input, okay, incoming voltage supply. So how are we going to vary this voltage? This is the use of the voltage regulator, voltage regulator, so that we can modify or vary the voltage regulator depending on the application or the output voltage requirement. So we will put the voltage regulator at the low voltage winding, obviously low voltage winding, because we want to modify amend the voltage supply to the low voltage winding, so that the voltage output will be can also be varies. Okay, the low voltage the primary winding ataupun we can call it low voltage winding. The voltage normally varies up to 200 kV, because this is the normal voltage that we supplied in the laboratory, in domestic appliances, and the high voltage output rating can be up as 200 kV RMS. This is 240 volt, a normal plug that we can plug the transformer, because straight transformer is a simple transformer. It's just a simple transformer. It's not a power transformer. It's just a testing transformer that been used in the lab, and that's why the incoming or the input rating up to 230 volt. Okay, there is a problem with the straight transformer. Okay, with a certain load capacitance, okay, if we use the transformer, this straight transformer, this test transformer connected to the load, in which is capacitance value, a certain value can introduce resonance. Okay, what is resonance? Okay, resonance occurred when the inductive reactance, where is the inductive reactance? Inductive reactance is from the transformers, from the coil, and the external capacitive reactance from the load capacitance. Okay, when we have inductive reactance equal to the capacitive reactance, in which omega L is equal to 1 over omega C, then we will have the resonance condition when inductive reactance is equal to capacitive reactance. Okay, what will happen if resonance? Okay, resonance, by its name we know that is the amplifications of the voltage level. Say we want to generate a certain voltage level at 100 kV output. When resonance occurred, the voltage can amplify up to 10 multiply of the original of the expected output. For example, 100 kV will become 100 kV will become 1000 kV, 1 mega, for example. That is the cause of the resonance. This is also an issue to the straight transformer. How to overcome the resonance problem? To ensure the load capacitance is not matched to the inductive capacitance. Okay. However, for resonance condition, we can use the resonance for other purpose. We can take advantage of the resonance phenomena for other purpose. I will explain later. Okay, the use of resonance conditions may result in higher voltage, test voltage being applied across the test object. As I mentioned before, higher voltage magnitude, And for another issues related to the resonance is that the fundamental frequency will be stressed out. Okay, the fundamental frequency will be stressed out, and this can also amplify the harmonic distortion. Okay, since the fundamental frequency is stressed out, and then the effect is that the harmonic can be a problem, distortion. Two issues related to the resonance. Okay. Okay, let's consider this one simple work example. A single phase HVAC RLC series circuit. HVAC RLC series circuit. Okay, it mentioned here single phase. Consists of inductance L equal to 75 millihenry, capacitance C equal to 1020 microfarad, and resistance, external resistance R equal to 0.3 ohms. Okay, the single phase supplied with the voltage V input, VI, is equal to 1.5 kV AC peak. Okay, so this value we normally need to convert into RMS. Okay, by neglecting any losses in the circuit, calculate the maximum current, Imax. Okay, how we can calculate the Imax? Imax can be calculated when we will achieve the Imax. Imax will be achieved during the resonance. As I mentioned, we will have the maximum current and maximum voltage, or maximum voltage during the resonance. Okay, the voltage overshoot, VL. Okay, overshoot, and then Q factor for the circuit occurrence at the resonance frequency condition. Okay, let's see for the solution. We go straight away, and then the given values here is L is equal to 75. We have the millihenry, capacitance 1020 microfarad, 0.3 resistance, and hence we can calculate the RMS values. 1.5 divided by square root of 2 will give you 1.06 kV. Okay. Okay, from previous slide we know that, okay, omega is equal 1 over square root of LC. Okay, omega, right? We know that omega is equal to 2 pi frequency. Thus resonant frequency FR. What is the resonant frequency? Okay, so we can actually calculate the resonant frequency. But why we first need to find the resonant frequency? As I explained before. Okay, sorry. Okay, as I explained before, the maximum current we can achieve only at during the resonance. That's why we need to determine the resonant frequency. How to determine the resonant frequency? We know that we can match these formulations, in which resonant frequency will become 1 over 2 pi. Rearrange this formula will give you these expressions, and then plug in the values will give you 18.2 Hz. Okay, this is the resonant frequency for this circuit. Okay, for this circuit we already obtained. Then we can calculate next the maximum current. Okay. Okay, again it's mentioned here because maximum current occurred at resonant frequency. Okay, during the resonant frequency, VL is equal to VC. VL is equal to VC. Inductive reactance is equal to the inductive capacitance, as I explained before. Thus, the impedance, okay, the impedance Z equal to R. Okay, so since this value is the same, so we can say that the impedance is equal to ZR. We don't need to calculate the value of inductive reactance or capacitive reactance, because this is during the resonance. the value is the same, and hence we can call the total impedance is equal to R. Alright. What happened next is that we calculate the I max. I is equal to V over R. So we know the value of V, RMS 1.06 kV divided by 0.3 will give you 3.5 kilo amp. Will give us 3.53 kilo amps. Alright, so next we look at the second questions, the voltage overshoot VL, voltage overshoot at resonant frequency. Okay, we know that VL is during the resonant, VL is equal to VC. Okay, VC, we can calculate the I max, I equal to reactant. Okay, reactant, inductive reactant, I max times inductive reactant will give you I max time omega, and omega is equal to 2 pi FL inductant. Okay, so we can plug in the values. We have everything here, including the I max. So this will allow you to calculate the value of the overshoot voltage during the resonant. So during the resonant, we will have 30.28 kV, and we have the current of 3.5 kilo amp. Okay, so during the resonance, we can conclude that the current will be magnified and the over voltage also will be amplified. Okay, so say for example we have waveforms. The waveform will be like this, a straight, and then during the resonance it will be overshoot. Okay, it'll be like overshoot and then continue with the normal one during the resonance. Okay, this is the problem to the straight transformer. And then we can calculate the Q factor of the circuit. Q factor of the circuit. To calculate the Q factor is actually Q factor at the resonant frequency is can be obtained by voltage divided by voltage overshoot divided by voltage input. Okay, in this case we know the overshoot voltage is 30.28 divided by 1.06 kV will give us 28.5 per unit, and we can round it to 29 per unit. Okay. Okay, what to do if the questions ask if the questions are the new Q factor of the circuit at 60 Hz frequency conditions. Okay. Okay, so in this case we need to know that VL is equal to VC equal to I max. Okay, this is very important. We need to remember or to use this formula. VL is equal to VC equal to I max 2 pi FL. I max, I maximum at the resonant frequency. So if we change the parameter, you should be able to manipulate the formula to calculate. Okay, and then the second we come that's done on the what we call it sorry. Sorry, it's loading. I don't know. Okay, it's done with the single straight transformer, and now we come to the cascaded. Okay, why do we need the cascaded transformer? Okay, means that we have the single the straight transformer, but what happened is that this transformer can only generate voltage output up to 100 kV. What we need to do? Okay, this the limitation of this straight transformer is 100 kV. So in order to generate for example 200 or 300 kV, we need to cascade, we need to combine this insulator, this single transformer in series. That is what meant by cascaded transformer. So why we want to do this way? Why we want to cascade the transformer? Why we want to combine this small transformer to generate a higher voltage level? Okay, one is that one reason, instead of having one unit that can establish 300, as compared to we have the 3 unit, the small one, to generate the 300 kV. If we go for one unit to develop for the 300 kV, we going to spend much more money for that, for the construction and we need more clearance, we need a more good insulation, because it's a higher power rating. So that's why we need the good insulation, and that will bring the cost for the relatively higher power output to spike. Okay. I don't read this. You can read by yourself or from my understanding, from my explanations. Okay, for each single unit having three, there are generally 3 main windings. Okay, we have the voltage. Okay, we have the high voltage, and we have another one is the exciting winding, right? These are the 3 types of windings at the for the transformer. And okay, for the construction, the low and high voltage winding follow the auto transformer concept. Okay, auto transformer, what is auto transformer? While the exciting is used to supply the low voltage potential to the next low voltage winding. Okay, we have one straight transformer, 2 and 3. We have 1, 2, 3 straight transformer. This is transformer, cylindrical shapes. Okay, the use of the exciting winding is that the exciting winding is required to supply the voltage for the next one. Okay, in which the low and high voltage winding is just connected to the other transformer by using the auto transformer concept. They just connected to each other, but the supply from the excitation winding will be required for each subsequent subsequent transformer. Say for example, if we're going to have 5, we need to have 5 excitation windings to the transformer. Okay, let's consider this representation, cascaded transformer. This the illustration of the 3-stage high voltage alternating current cascaded transformer. Okay, this is stage 1, stage 2, and stage 3. And this is the circuit representation 1, 2, 3. Okay, means that one straight transformer is combined with another one and another one, 3 of them all together. And the arrangement of this, if you look carefully, this is low voltage supply connected, and the second connected to the ground, and then this is the secondary windings connected to the ground, and we try to maintain the secondary winding of each straight transformer is connected to the ground. The reason behind it is that we want to provide the excitation winding to be 1 volt with respect to the ground. And then for the second one, the voltage difference between the second transformer to the earth will be 2 volt, and the third one will become 3 V. 2 times, 3 times. Okay, so if you can see carefully here, this is the illustration to illustrate the transformer. This is straight transformer 1, straight transformer 2, straight transformer 3. We cascade them together. We connect them in series, and then we will have, say, 1 kV will generate 100 kV, right? 100 kV. What will happen is that 99 kV here will feed into the primary of this one, and 1 kV. Okay, 1 kV out of 100 will be fed as the excitation winding. Okay, excitation windings. Okay, wait. So next, on the next level, we're going to have 200 kV at this one, and 199 will be fed into the primary, and the 1 kilovolt will be used as the exciting windings. So on and so forth. Okay, at the end of this 3 cascaded transformer, we'll have 300 kV HV output. Okay, concept of stage 1, as I explained before. I don't want to read this again. Okay, the low voltage winding is connected to the primary winding of the second transformer. Low voltage winding will be connected to the low voltage winding of the first transformer. This is the first one. Okay, and also high voltage is grounded to the tank. Okay, high voltage winding is connected to the connected to the tank. Okay, take note of this one. The exciting winding of this stage supply 1 kilovolt, as I explained before. 1 kilovolt to the low voltage winding of the second stage. Okay, this is just exactly what I explained before. Okay, and high voltage winding in this stage connected to the stage 1, connected in series, so that the voltage 2V is produced. 2V is not 2 volt, is 2 times of the voltage output. Means that once we have a voltage output of the single straight transformer is 100, so 2 times V, so we will have 2 times 100. So means that this is the reason. The reason we connect them in series, so that the voltage level is 2 times V. V is the output voltage of the first one. Okay, available at the next insulator. 2 times 100 equal to 200 kV. So the tank of the second stage must be, okay, bear in mind, okay, this is things that you need to know, in fact, that the tank of the second stage must be insulated, right? This is the idea behind it. Okay, the first one we connected to the ground, the second, the third, the fourth, the fifth, and so on is not connected to the ground. They must not be connected to the ground. Why? Okay, why? Because we want to establish the second one to be 2 times of the voltage, 2 times 100. We want to establish the third one to be the 3 times the voltage, 3 times 100. If we connect it to the ground, each of them will produce only 100. Okay, so that's why only the first tank is connected to the ground, and the second, third, and so on is not connected to the ground. They are connected to only to the first transformer, in this case insulated from the earth. Okay, concept for stage 3 is similar to the one in stage 2, so on and so forth. So what most important is to introduce the cascaded transformer in which in series connection, so that we can actually generate the 4 times of the output of the single voltage, 5th time of the output, 6th time of the output. So we can achieve a relatively higher voltage level by combining 2 straight transformer. That's it. That is what is cascaded transformer. This is how we generate the high voltage. First, by using the transformer itself. So we don't want to go to have we have like a bench size of the transformer with the power rating of 100 kV, output rating of 100 kV. So we don't want to have a one big one to produce a 500 kV. We don't want that because we don't want to spend much money for that. We don't want to spend much money for the insulation, for the space, for the testing laboratory size, for the clearance. We only, if we need 500 kV, what we'll do, we will just combine 1, 2, 3, 4, 5 of the straight transformer. That is the idea how to generate voltage by using the cascaded transformer. Now we come to the third one. The third one will be a resonant transformer. Right, for the resonant transformer, okay, for the resonant transformer, why we use the problem, the so-called problem of the single state transformer as the advantage. We manipulate the issues on the straight transformer to become a solution for other issues. Okay, means that we use the resonant transformer to overcome shortcoming straight transformer. Okay, first, as I mentioned, the resonant will amplify the magnitude, right? Okay, so we will use this one in case we really need to generate a high voltage level and we don't have the enough cascaded transformer. So what we'll do, we will use the resonant transformer concept to generate a much higher voltage level due to the resonant amplify the voltage, amplify the current, right? Okay, so we take it as we manipulate the problem to become a solution. In this case, first, we want to reduce the voltage supply. Since, okay, what happens since the resonant will amplify or magnify the output voltage, so we just need a little voltage input to obtain a certain voltage output, right? So we can actually reduce the voltage supply. That is the advantage if we use the resonant transformer. And the second one, the issues previously mentioned, it will put the stress on the fundamental frequency. Okay, in this case, we want to ensure a pure 50 Hz is delivered, because during the resonant, okay, what happened during the resonant, only the power or certain frequency or power frequency will be, the fundamental frequency will be stressed out, will become tangible. So in that case, we want to ensure, in this case, in this application, we want to ensure a pure 50 Hz fundamental frequency from the transformer. So we want to address these issues. Right, and then how we achieve the resonant transformer. The resonant transformer, this is the text is just what I just explained to you. I don't read this. It just reduce the maximum requirement for from the voltage winding of the supply. That's why I said, as mentioned before, to reduce the number of power requirement. And resonance can be achieved by using a series of parallel inductance. Okay, this is how we produce the resonant transformer. Okay, let's consider this configuration. Let's try to consider this configuration, and we know that resonance will happen when the the capacitive load is equal to the inductive load delivered by the transformer. So this is the configuration for the resonance transformer. So series resonant and equivalent circuit. Okay, we have this equivalent circuit. The RL is from the transformer, and CB is from the capacitance, is from the load. So we have the voltage regulator, so that this can be varies. So this will generate the resonant transformer. Okay, let consider a simple example here. A single phase HVAC. Oh, sorry, this is just the example that we attempt before. So maybe you can apply by yourself. Try to calculate the values, and then try to calculate, and we will discuss later. And then this is again this almost identical work example. You try to find yourself to obtain the solution for this one. Okay, the new Q factor, the new Q factor of the circuit occurrence at 60 Hz frequency condition. Okay, we calculate the Q factor. And how about calculate the new Q factor if the circuit occurrence is at 60. So what you need to do, you manipulate the formula here. Okay, where is this right? Which one? Sorry, it's hang. Okay, this one. What you can do to calculate the Q factor is just you amend this frequency voltage. Instead of that one to be 18, so we change it to be 60. That's it. And then you should be able to calculate the new Q factor. Okay, let's just scroll back to this tutorial. Okay, exercise 2 and exercise 3. Okay, analyze the working concept of 2 volt for 400 kV AC cascaded transformer together with its appropriate circuitry arrangement. Okay, how are you going to achieve? How are you going to achieve 400 kV of cascaded transformer? This to achieve the 2 times V. 2 times V, 2 V's. How to achieve this? By using cascaded. You can include the circuit representations. You can include the schematic diagram, and please explain how to generate or produce this kind of voltage output. Okay, now we look at the generation of high voltage direct current. Okay, how are we going to produce DC? Okay, how we introduce DC is solely by using the diode. Okay, by using the diode and smoothing capacitor. That is how you produce the DC. For in this topic, we're going to see the principle, how to generate HVDC, and how to use the HVAC transformer to convert the HVAC into the HVDC via the rectifier circuit. Rectifier circuit consists of diode and capacitor. Okay, for this one, we have 4 types. Okay, 4 types of HVDC generator. Okay, we have 4 types. First, we look at the half period rectifier circuit. Okay, we have the straight transformer here connected to the diode and the smoothing capacitor, and in parallel to the smoothing capacitor we put the load. This is the load. So we will achieve this one in terms of half period rectifier circuit. Okay, we can use this one. Okay, in case okay, this is the explanation. The smoothing capacitor is to reduce the ripple factor, to reduce the ripple factor here. And then this is the no output waveforms. Okay, no smoothing capacitor cause large ripple factor as seen on the load. Okay, we have the diode. Okay, rectifier. And then we have the sine cycle. Since we have diode, it will not conduct this one. And then we'll have the third cycle. The fourth will not conduct because of the diode. And then hence will give us these values. Okay, Without the smoothing capacitor, without this capacitor, our DC will become like this. So the ripple factor is too big. Okay, how to reduce, how to smooth it out is by using the capacitant. By include the capacitant. Hence, the voltage will become like smoother. It will become like this one due to the capacitor. The capacitor will discharge to the circuit, and then we will obtain this one, and so on. Okay, this is a half period rectifier circuit. Okay, how about the full period? Full period is just we have another diode. We include another diode here, D2, and then this we introduce this to the circuit, and then this will give us a full period rectifier circuit. Okay, how to achieve this? Okay, during the positive cycle, okay, during the positive cycle, the current, the flow of current will go this way, and then during the negative cycle, it will conduct this way, and this one block. Okay, so we have also the smoothing capacitor to smooth out the ripple factor, and if we can see from this one, from this circuit, we can see the ripple frequency is twice the value of the supply frequency, the ripple frequency. Okay, so we have D1 and D2. We include diode 1 and 2 to conduct one cycle, and the other one is to reduce for the other cycle. Okay, so we have this one. For half wave, we don't have this one. But for the full period rectifier circuit, we also will have this one because of this diode. And since we have the smoothing capacitor, so the waveform will become like smoother. So we will have a better ripple factor, and the ripple frequency is double. Is double of this one, the half wave is double. Okay, so means that if for the full wave, the ripple is this one is magnified, is double. Okay, so we will have the magnitude, the maximum value is higher for the full wave rectifier circuit. Okay, and then next is we going to see on the Cockcroft-Walton double circuit. Okay, what is that? What is Cockcroft-Walton? Okay, Cockcroft-Walton is actually the founder of this circuit to establish, to double up the circuit. Means that okay, for example, if we use the half wave rectifier circuit, okay, we want to generate 100 kV, maybe we will have a 90 kV if we are using half wave. If we are using full wave, we will have probably about 95 kV. Okay, if we are using full wave, slightly increase in terms of output voltage. But how about if we use the Cockcroft-Walton double circuit? What will happen is that the output voltage will be doubled. We expect to be 100, it's gonna be about 200. Okay, how this can happen? Okay, half wave produce a DC less than AC. Okay, the double circuit will double the circuit. Sorry, this is what I just explained to you. Okay, obviously the DC voltage, okay, as I explained, the DC voltage should be lower than the AC peak. Okay, AC peak, obvious. That is very obvious here. If the AC is 100, so the DC for the half wave should it may be around 90 kV. And if we are using the full wave, if the peak is 100, this one will be more or less about 95, slightly greater than the half wave, but slightly lower than the AC peak. due to the due to the ripple here. Okay, Cockcroft-Walton. Okay, okay, this is the circuit arrangement. Okay, the Cockcroft suggests that diode to be placed in this way, in which we have the capacitance here and here, and then for this we can actually obtain the voltage level as high as 2 times, double the expected voltage here. Okay, the arrangement of the diode is in these configurations. Okay, okay, as illustrations. Okay, diode D. Okay, what we have, what diode D1. Okay, diode D1 in figure 6b here prevent the voltage at point A from becoming a negative with respect to Earth. Okay, that's why it's double. Okay, because we have D1 here, that will prevent waveform to become a negative. Okay, point here to become negative because we have this one. So we during the negative cycle we will have a conduction in this way, and hence this one will not become a negative. Okay, so we will have a 0 volt at here to the twice the peak of the transformer at the output here. Okay, AC output is 100 kV, and then we will have the sinusoidal output will be 200 kV max. Okay, this is the doubler circuit, Cockcroft-Walton doubler circuit. This is how we manage to get the double. Right, next. Okay. Okay, the changing of the positive and negative half cycle of AC sinusoidal supply allowed depending on the voltage given, the conduction and non-conduction of this diode, charging and discharge process capacitance. Because the combination of the diode, okay, the arrangement of the diode, so first we prevent the negative cycle, and the second one is the discharge from the capacitance to magnify the total voltage output. This enable the production of DC waveform with an output of 2 times Vmax. Okay, 2 times Vmax. Okay, the produced DC waveform for having 2 max, no loading condition is shown in this figure. Okay, for example, okay, we have this cycle. This is the supply voltage. This is the supply voltage, and this is, okay, this is the waveforms of the Cockcroft doubler circuit, and this is the output voltage. Okay, it magnified by 2 times, and then hence we will have the Cockcroft-Walton doubler circuit, which is HVDC at 2 times of the supply voltage. We will have 2 max. Okay, this is Vmax, and then this is double, so we will have 2 Vmax of the DC circuit. This is the voltage curve under no load conditions. Combined with the load will be slightly different. Okay, now let's see. Okay, the voltage drop across during the no load conditions. Okay, the result voltage should be less, slightly less than 2 Vmax. Okay, so we expect to be 2 Vmax is this way, but it is obvious to the same like a full rectifier circuit, we will have a slightly lower than Vmax or Vpeak. So at no load voltage, we will have this load voltage VDC output. Okay. Okay, what happened during each cycle, the capacitor 1 replenish the charge lost by the C2 in supporting the load, causing V at node A, in the figure 6 to never attain potential plus 2 max. So it's a combination of discharge and replenish. C1 and C2 ni, this C1 and C2, one is discharge, one is regain. One is discharge, one is regain. So that is the scenario in which we will never achieve the maximum to max. Okay, we will never achieve due to this condition. One replenish and one is charging and replenish and the supply to the load. Okay, voltage drop during the load. Okay, during the loading conditions. Loading condition means that we put the external load in term of resistance that will never achieve 2 max. Two reason. Okay, two reasons. So read this one. Due to the combination of replenish and charging and discharging, and the smoothing capacitor, the ripple factor, due two factor. The ripple factor like a normal rectifier circuit, and the other one is the combination of C1 and C2. Capacitor 1 and capacitor 2 to discharge and charging, right? This that's why we will never reach the maximum value at this point, although we expect to reach this one, but due to these two reasons, the output DC will be slightly lower. And then the last one will be Cockcroft-Walton multiplier circuit. Okay, just by looking at the title, we know that the Cockcroft-Walton multiplier ni, this circuit can be combined. Okay, that can be combined to reach a relatively higher voltage level. It's just like a cascaded. We combine the Cockcroft-Walton multiplier circuit, and then that will give you a multiplier circuit during at no load condition. This is the arrangement. This is the Cockcroft-Walton circuit, this one. And for the multiplier circuit, we simply add on another circuit to the top. Okay, what we need to include is actually D1, D2, and C1 and C2. Okay, D1, okay, D prime, we call it D prime here, D prime, C and C prime. Okay, so we just multiply this one. This will simply give rise to the voltage output. Okay, means that this one, okay, figure 8b show two stage cascaded circuit. Cascade circuit of Cockcroft-Walton. The configuration produce output voltage at 4 Vmax. Okay, the Cockcroft-Walton doubler circuit will produce 2 Vmax, and if we cascaded 2, we'll give 4. If we cascaded 3, we'll give 6, so on and so forth. Okay, okay, end stage, okay, will give you n Vmax. Okay. Okay, we have the charging side for the smoothing column. Okay, for the smoothing column, and we have the charging side of the oscillating column. So this one is n-1, n-1, -2, so on and so forth. Okay, so this is n1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Combination of this smoothing column and the oscillating column will give us a Cockcroft-Walton circuit that generate the N of Vmax. Okay, what is the problem? Okay, what is the problem? The voltage drop during loading condition. Obviously, once we have the external resistance or loading, we will have a voltage drop. So every voltage multiplier stage that used in a DC add on extra voltage drop to the system. Okay, what happened? What happened is that each circuit will have each voltage drop. Okay, each circuit will have each voltage drop. If we combine 1, 2, 3, 4, and 5, we will have multiple voltage drop that will lead to the relatively high voltage drop at the output. Okay, say for example we have 10 kV, 10 kV, 10 kV, 10 kV, and at the end of the circuit or at the end of the output, we're gonna have about 10, 10, 10, 5, 50 kV. As simple as that. So the more circuit we cascade, the more losses that will experience, or the more voltage drop that we will experience. So the best practice is to use only 5 stages, up to 5 stages, for economic and effective. Maybe greater than this will be not effective for a laboratory purpose, testing, and to be used in the lab. Okay, I think that's about generation of high voltage, AC and DC, and we will continue generation of impulse in the next section, inshallah. Okay, with that, thank you. Assalamualaikum warahmatullahi wabarakatuh.